So please, if you haven't reached out to me yet, please do. And for those who did, I have either responded to you, I will respond to you right after class, so that we can schedule some time for meeting about the course project. But please do so over the next, like you have today, you have tomorrow. The document that you're submitting on Friday is basically a one-page document. It's not that big of a deal, but to be able to submit it, I need to know beforehand what kind of project idea I have in mind. Any questions about the course project or the seminars? I'll just wait a few more seconds just in case somebody's typing up something on the Zoom link. Okay. All right then, if you do, please reach out. Like I said, I'll be happy to help out. So continuing with our topic from last week before the long weekend, we were discussing IFDS, the Interprocedural Finite Distributive subset of problems, the framework that allows us to do interprocedural data flow analysis, which I consider to be the interprocedural counterpart of the monotone framework. One of the things that we were talking about towards the end of the lecture last week was various configurations that affect how data flow facts may be computed in IFDS. The first step in IFDS, as you may recall from last week, is we first have the interprocedural control flow graph, ICFG. You annotate the edges with flow functions, you get the exploded supergraph, ESG, and then you start propagating data flow facts along the paths that you have in the program, starting from the tautological fact, or 0, from the main entry point of the program, all the way until you reach a certain point. You have 4 different types of flow functions. Normal flow functions for intra-procedural data flow, meaning statements within the methods. At any of those statements, if that statement is a call site or calling a method, you have to define 3 different types of flow functions: call flow function, return flow function, and call to return flow function. And these capture the way information or data flows from the caller to the callee and back, and other values that are not related to the call itself and how they're going to be propagated forward after the call. At merge points, you have to define your merge operator to be able to merge facts from multiple paths. And this is how we can support data flow propagation across different paths in the program. One of the things that we ended our lecture with last week on Thursday is how does handling fields may affect data flow propagation. And if you recall from previous lectures, we have 3 different main techniques to handle fields in program analysis. One is field sensitive. You differentiate the reference that you're using as your local variable for the field access and also for the fields. Field insensitive, you don't care which field you're accessing, you only care about the object that you are dereferencing. Field-based, you don't care about the reference you are dereferencing, so you just use the type, the name of the type that represents that object, but you do differentiate between the fields themselves that you're accessing. And then we had a few examples where basically in the first example we had a field-based version of IFDS, where the domain of the analysis is basically local variables and fields. And in that case, we found that because in the analysis, because we are going to use field-based, so the field axis b.f is modeled as ds.f in our domain. So if b.f is tainted in our taint analysis, assuming this is a taint analysis problem, then c.f is also going to be tainted just because I don't differentiate between C and B as receivers or as locals used to access or dereference a field F. So in that case here, both D and C.F, which is ds.f in our analysis here, computation will be tainted. This is opposed to field-sensitive analysis, where the domain of our analysis is a little bit more precise. So here we define our domain to be all axis paths, basically, or field axes, such that L is a local variable, and all those f of i's fields that I'm accessing are one of the fields that we have, and you can access as many fields as you can. So in this case here, B.F is going to be modeled in this abstraction, in this domain, is going to have its own node in the exploded supergraph. C.F will have its own node, but I don't need to represent it here because, remember, from the on-the-fly ESG construction, we only create nodes and edges for those facts that are actually propagated. We don't create all the nodes and the edges from the beginning, but only for those as we propagate them. And in that, using that more precise abstraction for the domain here, we are able to say that C.F is not going to be tainted, which means D is not going to be tainted, and I don't need to represent them in my exploded supergraph. This is what we ended our lecture with last time on Thursday. One thing that we have here that's a bit of a problem is this little limit, or rather no limit, on the number of fields that I can access on this local variable L. This pretty much says that our domain is going to be infinite because I can have as many field axes as possible without having any limitation on the length of the axis path. So this may cause our analysis not to terminate. And this is going to be a problem. So how could this be a problem? So let's have an example here. But before I go into that example, does anyone have any questions about that quick recap of IFDS? Because I'm going to build on top of that for the subsequent examples and also for the second topic that we're going to discuss today, which is IDE. Okay, so we have to agree on something here, folks. When I'm asking a question specifically, that if you have any questions or not, I do wait for your answer. I know that almost all of you, and not only in this class, do not prefer to use the voice chat or have your videos on, and that's fine. But please do respect giving me some response for those questions, because otherwise I don't know if you can hear me or not. I don't know if you have a question or not, because I can't see your faces, so I can't tell from your facial expression whether you're confused about something that I discussed in the class or something doesn't come across, which would make me typically in a physical class just stop, re-evaluate, and then explain things further. So please, if you don't have any questions, also indicate that, at least by typing up something in the chat, because otherwise I will just be stopping here for a couple of minutes without having any positive interaction in the class. So you do see a question there. Is making the first node self-referential just a convention, or is there some sort of more important meaning here? I'm guessing that you're referring to this node here, right? Like the tautological fact 0. Okay, so from our lecture last Thursday, we do that in order to bootstrap the analysis, because otherwise, if I just say I'm going to start from the tautological fact 0 and then go to A, well, how am I going to bootstrap the analysis, the algorithm, such that I know? Because remember, like the key thing or the key feature of IFDS is it reduces the analysis problem to graph reachability. So what does it mean, graph reachability? It means that I have to compute some path along the way in my exploded supergraph. But to be able to get that first node of the graph, I have to make it reachable from itself, such that I can bootstrap my algorithm that will start solving that graph reachability problem. And if I don't have that, there is no way for me to determine how that initial node is actually reachable itself. So we do that for the tautological fact, and we also do that for the arguments of methods when we go from using the call flow functions to be able to compute the call flow functions properly. So we also, at arguments of methods, we have this self-referential edge. So it's not a convention, it is something actually quite important that bootstraps the whole analysis. I hope that answers your question here. Alright, so let's actually go back to the example when I started, when we started actually talking about this. So in our previous lecture, I'll just take this example here. So in this example, in the naive way to construct the exploded supergraph, so what did we do? We just said, okay, we are going to extend our edges. Maybe start from here. We're going to extend our edges anyways, beginning from the very first statement of the program, and just keep extending the edges, and then create nodes for all variables that we have. So that's why at this point in the program, even before executing a equals password, we have a node. We have a node for 0. That's the logical fact. We have a node for a. And we have a node for B, even though I haven't even hit A or B yet, but I have them. So I'm going to create nodes for all variables. And I'm going to create edges, propagate them forward, those 3 edges here, just to say that, yes, those variables are going to be reachable from those nodes, because nothing has affected the fact that A is reachable and B is reachable. But then I also generate actual edges here due to the flow functions that I have defined, which means A is going to be reachable from the tautological fact 0. So that is fine. So the main thing here is that I am going to create nodes and edges for all variables. I'm going to propagate edges forward as long as the flow function does not indicate that I have to remove that edge. So that's why in the next step, I propagated that edge forward, propagated that edge forward. I removed that edge. I did not propagate it forward because the statement B equals 0 says that I'm overwriting the value of B, whatever it is, with the value 0. So that means that after this statement, B cannot be tainted. So there should not be an edge here. It doesn't matter what happened before B, before that statement. I don't care what happened here, but this edge should not exist. So now I'm not going to propagate it forward. However, when I have my next method call, so I'm calling B equals foo of A. So foo of A means the following. Well, 0 is always going to propagate to 0. A is going to propagate to P because P is the argument of that method. So I have that edge here. And here I'm going to do the same thing. I'm not going to propagate that edge further because the first statement here is P equals 0. So I'm basically what the flow function of that statement will say is I'm going to kill or not remove, I'm going to kill or remove the propagation of the edge, this edge here, because P is being overwritten by 0. So it should not be tainted in that step. And so on and so forth. So you can see here that there are some edges that are unnecessarily being created and nodes that are unnecessarily being created in the exploded supergraph, because this is the naive way to compute it. So, and this is indeed true. So if we fast forward a little bit, we'll see here that some of the edges that do not make any sense is this node and edge here. I shouldn't even have that in my graph. And this path here. this whole thing here, I shouldn't have this in my exposure supergraph because it's coming from nowhere really. So why would I have it there? And maybe even P, why would I even have it there? It doesn't go anywhere. So I shouldn't have them in my graph. So indeed, this is what we actually do in the on-the-fly exposure supergraph construction. So in practice, the algorithms in analysis frameworks do not follow this naive way of constructing the exposure supergraph, but rather follow the on-the-fly construction. So what does the on-the-fly construction say? It says, well, first, what is the goal of IFDS? The goal of IFDS is to find whether a node is reachable from this tautological fact 0 or not. So the first thing that I have to start with is the initial tautological fact 0. This is always going to be reachable. So I'm going to start my construction with it before the first statement. And to initiate the propagation of the data flow, I'm going to say, well, the data flow of this edge goes to itself. So it self-initializes, it bootstraps itself. It is reachable from itself. Because any node that is going to be reachable has to be reachable from the tautological fact. So it has to have this self loop to begin with for it to be reachable. For the definition of that node to be reachable from the tautological fact 0 to be true for all nodes. And then we're going to go forward. So this tautological fact is always reachable from the initial tautological fact. So that's why we have this edge. And then we create that edge because A is equal to password. So that is tainted. I don't create any nodes for B. So, and then we compute the path edges, compute our data flow further, or propagate our data flow, compute more path edges or extend our path edges. We have our method calls here. Once we have the propagation, once we create our path edges, we just ignore those intermediate edges as we go. Here again, as I said, for the method calls, we start, for methods, the beginnings of the methods, the arguments of the method also have this self-initial loop so that I can start propagating the facts from those arguments further. Because you have to remember one thing here. The way we are going to analyze the methods in IFDS, like I'm not always going to start analyzing them from the main entry point of the program to other methods, or even if I started from the main entry point, the order for which I'm analyzing the methods is not the same order every time I analyze my program. So at one point I might analyze foo first before I analyze main or before I analyze bar. And for me to propagate any data forward to compute the method summary of a method, I have to assume that the arguments are going to be reachable. And then figure out based on the flow functions whether I should propagate facts further or not. And for me to do that, the only way to assume that is to make sure that the arguments have those self-initial loops. And the tautological fact of that method to have its self-initial loop. Then I can actually, based on this initialization, decide whether I should propagate that data flow further or not. In this case, I am only propagating this data flow fact, but not this, because of that statement P is equal to 0. And this way, my summary for that method will be that path edge here, nothing else. And then I will continue back with my propagation as such. And eventually, this is going to be all the path edges that I'm computing. So, long story short, the reason of this self-initial loop is to bootstrap or start the data flow propagation at the beginning of the method before knowing anything else about the statements of the method. And then the flow functions as we go will determine whether this propagation will be, whether these data flow facts will be propagated further or not. So I hope that clarified things a little bit here. Okay, cool. Sounds good. So I'm glad we got this sorted out, because that will have an effect on the following part of the lecture. So as I was saying, in a field-sensitive analysis here, one of the caveats of this definition of the abstract domain is we don't have any limits on the length of the access path that represents that field axis. We are just saying here that our domain is L.f of I for f of I to n, where n is greater than or equals 0. So I can basically have an infinite access path. Problem with that is you have an infinite domain, does not terminate, not good. So how can we work this out? Before I tell you how to work it out, let's have an example. So in the previous code, this was a straight line code, so the problem might not be that obvious. But here we have a while loop where the condition of the while loop depends on something random. So it might be some user input, some evaluation of a condition, reading a file, a configuration file, something that is not deterministic at compile time. So in this case here, we're going again to start with the self-initial loop. A is going to be reachable, and it's a field-sensitive analysis, so we have A here as our access path. Then in the first iteration of the loop, well, 0 is going to make A again reachable here. So I'm showing the path edges, so I'm not showing the intermediate data flow propagation, only the path edges. After this statement, B equals new DS, well, no problem there. B.f equals A, well, at that point, B.f has to be reachable because A flows to B.f. Then B flows to A, so at that point, the value of B goes to A, right? So the next point in our program, if B flows to A, then A.f will also now be reachable in the next iteration of the program. In the next iteration of the loop, because of that assignment statement here. Because if B flows to A, then whatever B points to, A will also point to. And if A is tainted, then it will taint, then from A.f I can also reach some tainted value there as well. So now A.f is going to be tainted. Then the next iteration, when I'm assigning, well, A.f is going to be tainted, B.f is going to be tainted still. Then from that assignment statement, B.f is equal to A.f is tainted. Then now when A is equal to B, now B.f is tainted, because I'm basically adding one level of dereferencing every time I go through the loop. Every time I go through the loop, I read the field F from B.f, or I drill deeper into the object F, in the object D, in the object B, with one more field access or dereference of F. So now B.f.f is tainted, and A.f.f is also tainted because of that assignment statement, and I can keep on going like that. So every iteration of the loop, you add one more access path with one more F, both for B and one for B and one for A, and they are both tainted. And this can go on indefinitely for as many iterations as your program will execute at runtime, which in this case, you don't know how many iterations that is, so you cannot even tell when your analysis will terminate. You cannot determine that at compile time or at static time. So there is only one way around this, really. And this way is we need to put some limit on that n here. We can't let n grow indefinitely. So this is the second time we see k-limiting used in our lectures here. So we are going to define some limit k, where that limit k is the upper bound of the value n. So here we're saying, yes, this can grow, but it won't grow indefinitely anymore. We're going to stop this growth up to a certain point. Let that be 3 maybe. So in this case, I'm only going to abstract until B.f.f, A.f.f. Anything that comes further, I'm going to be basically treating it as B.f.f.f.star and A.f.f.star. So I won't be able to determine how many more field accesses I have here in my access path. I'm going to stop at depth 3. You can even choose a lower bound for k. What does that mean? I mean, it comes at a cost, of course. So on one hand, your analysis will terminate because you have a finite domain. But the cost here is that anything that is longer than that length or limit k is going to be modeled imprecisely for the benefit of just having your analysis terminate. So you kind of pick your poison here. Do you want your analysis to terminate, or do you want to get some possibly imprecise results? I mean, the one thing that you can go around this to resolve this kind of problem or trade-off is choose a value of k that is big enough that will still make your analysis terminate, and it will still fit the longest access path that you have in your program. So if somehow you go through your program with a pre-analysis pass or something and figure out that, yeah, well, in my program I can only have the maximum depth for a field access is 2, then maybe 2 is good. Then maybe I can set k to be 3, and then everything will be fine. So k limiting in general is, yes, going to be imprecise, but if you apply it to a specific case where you beforehand, before analyzing your program, you know what the value of k that will support the longest field access you may have is that value, you can just set your analysis to be that value. You might think, well, is that really practical? Like, do actually programs have field accesses that are longer than 3, 4, or 5? And the answer is yes. So from experience, the Eclipse IDE, the development environment, does have some field accesses that go up to the size 13, the length 13, which means that in order for your analysis to model this field access properly, you have to have the value of k is equal to 13 or more. Worse than that, if you're dealing with any recursive type of data structure like tree, hash set, hash tree, or a tree map of some sort, this can grow up pretty quickly, especially if you're doing some search over that tree. So parent, left child, and you can do this recursively. You can go really longer than 13 really quickly through just parsing through that tree. So yes, you need to choose your k-limit carefully such that your analysis still terminates, but you still support the longest possible access path your program may have. So let's have an example here for k-limiting. So let's assume that our k is 2 in this case, or greater than or equal to. Here we have a straight line program, so no loops here. And I just solved a little bit of those nodes that we have in our graph. In our exploded supergraph ESG here. So we have a node for A, we have a node for B.F, C.F.F, D.F, and E. So if k is greater than or equal to, which means I can support C.F.F, I can abstract C.F.F properly, and I can abstract D.F properly, I will be able to say that at that point D.F is going to be reachable, right? And then E is not going to be reachable. However, if I set my k to be 1, that means I can still model B.F properly, but C.F.F I can't, because that would need k to be at least 2. So it will be C.F.star. D.F I won't be able. Well, that actually should still be D.F. And that is E.star, because I don't know how many values of E here I may, how many field accesses I may access E here. But in that case, I won't be able to. I won't be able to say that E is not tainted because of that over approximation, because of really this over approximation here, C.F.star. So at that point, that over approximation will yield a false positive in the analysis result. So even though it is the same algorithm, the same program, the same handling of fields, it's field sensitive, but a different value for the k limit yields a different result. So again, this is one of those analysis configurations that would affect the result of the fixed point solution that you get from the lattice of fixed point solutions. Any questions so far? All right. Sounds good. So a few more tidbits regarding IFDS. The first one is flow sensitivity, and we sort of get this for free with IFDS. Why we get that for free? Why do you think we get flow sensitivity for free here? Why does an IFDS analysis is flow sensitive anyways? So what is flow sensitivity about? How do we make our analysis flow sensitive? From 2 or 3 lectures ago. Maybe even more than that. Definitely more than that. So if I give you some sort of analysis and I tell you, I want you to make this analysis flow sensitive, what does that mean? Anyone? Yes, it has to respect the control flow of the program. So if your analysis respects the control flow of the program, then it is flow sensitive. So how do you respect the control flow of the program? How does the analysis respect the control flow of the program? What kind of graph it should follow to respect the control flow of the program? The answer is pretty much in the question there. The control flow graph, exactly. So in IFDS, if you recall, the exploded supergraph is the interprocedural control flow graph annotated where the edges are annotated with flow functions. So that's why we pretty much get flow sensitivity for free, because the graph that we are operating on is already a control flow graph for the whole program. So that's why an IFDS analysis will give you a flow sensitive result anyways. So now about context sensitivity, the way we're going to get context sensitivity in IFDS is through method summaries. That's pretty much what context sensitivity is when we discussed it last week. The idea is you want to create some sort of a model or a summary or an abstraction of what the side effects of the method is, and apply that side effect at multiple different contexts. And each time you apply that summary, you get a different result. So here is an example for you. You have some path edges that represent the data flow before that first call. You have the method summary here for that method. Once you're going to call it with the argument x, passed, so meaning that x is going to be passed to a, and if it is passed to a, it is going to affect this value or this data flow fact b, which means that b now is going to be reachable from our graph. When b is reachable from the graph, it is assigned to the value y, so it makes y reachable. So method summary, data flow fact, calling the method summary or applying the method summary that yields a result. Then I'm going to propagate things forward. Propagating things forward will make y reachable. 0 is always reachable. Now with the second call that I have, I'm calling the same method. Here I'm calling y as my b in the second value. So I'm calling the same method but with different arguments. So maybe the first time I was calling it with xy, the second time I'm calling it with yx. And now y is being called here to b, but when it's called, when it's passed as an argument to b here in this method call, b is not propagated forward, so I'm not going to have a back edge here, so which means this propagation is going to be killed. So y is reachable only at that point, but not reachable at this point here, while the tautological fact is still reachable. So same summary, same method summary, different values for the call in the first call here than the second call give you different results depending on the context. And this is what really context sensitivity is about. This is how you get context sensitivity in IFDS, through the creation of method summaries and applying them in different contexts depending on the values that you have. So the main goal of an analysis engineer when they define an IFDS problem is being able to have a finite domain such that your analysis terminates, specifically k-limiting. Flow sensitivity is pretty much given for free. Properly defining your flow function such that you're able to create method summaries, because that gives you context sensitivity as well for free. Large domains, like I said, may cause performance problems, may even make your analysis not terminate. Any questions so far? All right then. Sounds good. So what if we have a large domain anyways? What if I'm trying to do an analysis of some sort that just requires a large domain? So I'll give you an example. So here we have r equals v plus 1, and I want to do a linear constant propagation. A simple linear constant propagation example. So if I'm creating the method summary for this method, and the method basically is just literally that single line, that single statement. So 0 is always reachable. I'm passing an argument 0 as a parameter, so v and 0 will be reachable. But then v and 0 will make r and 1 reachable, because r is now going to be constant and its value is going to be 1. So I'm not doing taint analysis here, I'm doing constant propagation. And in any context of that method, this is basically the method summary here. In any context, so the context independent summary of that method is, if v is 0 before the call, v is still going to be 0 after the call, but r is going to be 1 after this call as well. This is that method summary here. So let's say this is going to be the inc or the increment method here, and I have a main method where I'm calling inc first with a value 1, then I'm calling inc with the local variable x, then calling it with y, then I'm printing the value z. So what this would look like here. So first v0 and r1, then the next time I call the method, I'm going to get v1 and r2, then the next time I call the method is going to be v2 and r3, then the next time is going to be v4 and v3 and r4, and so on and so on and so on. So I won't be able to represent this kind of large domain using IFDS, because the abstraction that we're using here for IFDS just doesn't work for this large domain. So instead, we're going to use, or we're going to define a different framework called IDE, the interprocedural distributive environments that can abstract further away from IFDS and flow functions to an abstraction level that allows us to define environments rather than just flow functions. And I'm going to stop here for a few minutes midway through the class, and when we come back after the break, we're going to go through the abstraction of IDE, how do we define an IDE problem, and how different it is compared to IFDS. So let's reconvene at maybe 1:17 or 1:18 Edmonton time PM, And once we're back, we're going to talk about IDE and how we can abstract away from IFDS as such. Thanks, everyone. Talk to you in a couple of minutes again. Alright then, welcome back everyone. So let's continue our discussion from before the break. So before the break I was talking about IFDS and some of the problems or issues with it. So just to give you a quick idea about the complexity of IFDS as an analysis, the algorithm itself. So the complexity is here big O of the number of edges you have in the exposed supergraph, because you have to analyze those, multiplied by the size of your domain to the power 3. So which means if this domain here is of infinite length, then pretty much your complexity is infinite and you won't be able, or a very large even domain, not just infinite, is if the domain is just very large, then your analysis will not terminate within a reasonable amount of time. So even though that most problems can be encoded in IFDS, most analysis problems, it might not be the most efficient representation. One other limitation is the merges here are restricted to unions. Remember, like if you have a merge, your merge operator has to be the union operator. That's why it's subset problems. So if you want to define anything where the merge operator is not a union, you can't use IFDS for that. If you have something with a large domain, you can't use IFDS for that. So as in before our lecture, we were saying that linear constant propagation is an example here that shows all these problems with IFDS. So linear constant propagation as an example that shows all those problems with IFDS. The domain is quite large. We have almost all natural numbers in there, or all integers numbers in there. Merge has to remain set union. So union here does not discard any values, so just keep accumulating values as you go, which doesn't give you the most precise answer to linear constant propagation as you would like it to do. So what is really the essence of the problem here? So what is the essence of the problem here? So the essence is that from the example that I showed you before, the essence of the problem is that the summaries grow indefinitely, basically, or grow with rather any new input. So the more the new input that you get is gonna grow your summary, the method summary, further. That example that we had with r equals v plus 1, so you're gonna get v 0 and r1, v1, r2, and so on and so forth, right? So because that domain is very broad, I mean, some of you might say, well, if we know the language like Java or C, we know what the maximum integer that is allowed, but still, that maximum integer, you can have your domain as top and bottom, and you have 1, 2, and 3, all the way up to max int. That's still big enough that would make your analysis actually suffer performance-wise. And like I said, your merge operator here is only union, therefore you cannot apply more sophisticated merges here. So let's say, for example, that you want to say, well, the domain of 1 and 3 merge, I don't want to use this, there we go, merge 2 and 5 is going to be, well, I don't know, is going to be probably 1 and 5 or something. Or maybe you want to say 1 merge 5. So what do you want to say here? What would that be? Would it be 1 plus 5? I don't think so. It would be maybe the range 1 and 5, or 1 to 5. Or maybe you want to say the range 1 to 10. So these are going to be difficult to define using only the union operator as your merge operator. And even worse, if your language says that the max int here is infinity, then basically you really cannot encode even this in IFDS. So the solution to all these problems is going to be IDE. So IDE is your solution here. And the reason why it is going to be your solution is that it is an inter-procedural distributive and I'm going to inject here saying finite also environments. No worries there. Good luck. It's an inter-procedural finite distributive environment problems. So it is environments instead of subsets, like with IFDS. So what does that exactly mean? So let's go back to our example here with the constant propagation example that we discussed from before. And in this example here, we're going to say the following. So that example was the method inc v with r equals v plus 1 and return r. So if we are doing this using IFDS, this is how it is going to look like. Sorry, just give me a second here. If we're doing this using IFDS, this is how the method summary is going to look like. So the summary here is going to look like the following. vn0 goes to vn0. vn0 goes to rn1. vn1 goes to vn1. And vn1 also goes to rn2, and so on and so forth. While the tautologic effect always goes to the tautologic effect 0. In IDE, what we are looking for is how can we abstract from all these summaries here to one single summary that basically says the following. Well, v of I goes to v of I, whatever that I is, and v of I would be mapped in the new environment to something that would be I plus 1, and 0 again is going to be mapped to 0. So this is the encoding that we want. This is the encoding that will be not infinite like this one. These should be R's. All these should be R's here. But it will be basically a function or an environment or a collection of elements in this environment that abstract from all those values here. I'm going to abstract away from all those values to only those three statements. So the idea here is this here is going to be context independent. It's still going to be context independent, while the value of I is the value that will be context dependent. So depending on the value that I pass along to the function, we are going to get a different result from applying that constraint. So the idea here is, if you recall from our time with the monotone framework a long time ago, And also with IFDS, like we annotated the edges with functions. So what would be the function that I would use here to represent these facts in IDE? So forget about the IFDS functions for now. But what would be the function that if I want to annotate the edge or to use as a summary for that function inc, what would be the function that I have here based on these data flow facts, these data flow facts in that rectangle here? What do you think the function would be? So what does that function inc does to its input, to the argument? It increments a value and returns it. So if I want to apply a function, I'm going to say, if I have a function of I, this is going to give me back I plus 1, right? That's exactly what this function does. So what if there is a way for me that says, define a function that basically does exactly that. Given an I, I'm going to return to you I plus 1. And then use that function to annotate the edge in the exploded supergraph. And then somehow come up with an algorithm that can solve for all these functions, for all those function applications. If I'm able to do that, that would actually allow me to represent an environment of all the values that I would have represented in IFDS, but represent them in their abstract sense. So let's move forward with that definition and see how we can actually get this done on the same example here. So if I want to say, let's annotate the exploded supergraph. So here we have 0, that's a tautological fact. Here we have V, and here we have R. And I'm saying, well, here 0 is mapped to 0, no problem. V of I is mapped to V of I, again, no problem. V of I is mapped to I, Ri plus 1. So basically I need to have other nodes for after the statement. 0 is mapped to 0. This is no problem because this would have 0 mapped to 0. V of whatever is mapped to itself again. And then V is mapped to R. So how am I going to annotate those edges with functions? So watch out for the notation because it's something that we might have used in the monotone framework, but not necessarily. So that notation might be a little bit new to you. So if I want to annotate that edge with a function that will cause this data flow to happen, what would be that function? What does that function do? The function that whatever input it gets will just return the same as an output. What kind of function is that? We discussed that when we talked both about IFDS and also interprocedural analysis. A couple of times. What is the function that, given an input, returns the same as an output? There's a specific name for that type of function. Yes, identity function. So this here is the ID function or identity function. This here is also the identity function. And this here is the function, or lambda, given an I, will just return I plus 1. So this ID function is basically I will just return I will just return I. So I'm gonna use identity function for both this edge and this edge, but for that edge I'm gonna annotate that with the function lambda I equals I plus 1. Increment the input I with I plus 1. So in IDE, to be able to create or the algorithm, for the algorithm to operate, it operates in a slightly different way. So it operates, instead of one go, it operates in two phases. Phase number 1 is the following: create context independent information. And once you do that, we can move on to phase 2 of the algorithm, where you compute the context dependent information. So think of it as, in phase 1, you're trying to create the method summaries. And in phase 2, you apply the summaries to compute the result of your analysis. The other thing that we are going to do here is we are going to give a different name to our tautological fact. So instead of this value 0, we're going to use the conjunction value, which is going to give it that operator name, or that symbol here, to say that this is our tautological fact in IDE, because we are operating on environments of functions, so we have to use function symbols here. And this is going to be our IDE algorithm. Any questions so far? I'm still going to go through an example of IDE on the same program actually that we just had, and then going through how we can construct those summaries and how we can annotate those edges with summaries. All right, so no questions yet. All right then. So knowing all that, let's actually apply this on some example. So the way we're going to apply this is the following. So here is our example. And this example is going to have t is equal to 0, x is equal to inc t, and then y is equal to inc x, and then I want to print out the value of y. And the function inc has the following statements in it: r equals v plus 1, and then return r. And in the middle part here, I'm going to have our data flow. So before that statement, well, I'm going to have my tautological fact, and then I'm going to have t. So here, before that statement, I have these two nodes here. So how am I going to do this? Well, before the fact and after the before the statement and after the statement, I have the tautological fact still holds, and I'm going to have ID, identity function. So I'm going to use the acronym ID to represent the identity function. Now, what happens after this statement? So here I'm doing linear constant propagation. And if I'm doing linear constant propagation, it means that if a node is reachable on the exploded supergraph, that means it is a constant, and I know its value because of the way these statements are flowing. So after this statement, t is equal to 0, what would be the connection that I would have here? Which nodes should I connect to each other? So basically, if I look at this code again, I would say similar to IFDS. If we're doing this in IFDS, and I want to say, where would this node be reachable from after this statement? If I'm doing linear constant propagation, you would say, well, t after that statement is known to be constant, and it has a known constant value, so it should be reachable from the tautological fact. So similarly, this t here should be reachable from my tautological fact here, right? But in this case, we would have a different annotation on the edge, because we're going to have our functions as edge annotations, and here the fact would be that whatever I you're getting in is equal to 0. So the input to that function, whatever the input is, you're going to get a 0 as an output, because t is equal to 0. This is going to be the function that represents the side effect of that statement. The input that you get, you're going to get 0 as an output. Is that clear to everyone? Okay. All right. So the other thing that we're going to have is we're going to propagate this forward to right before the statement, the next statement. Again, propagate this forward to right before the next statement. I'm going to hit that statement x equals inc t. What does that mean? Well, that means I have a flow, I have an interprocedure flow. So I'm just going to do the same thing like I did with IFDS. So I'm going to have, for that method here, I'm going to have my tautological fact before the statement. In that method here, I have v, and I also have r here. Tautological fact will flow to that other tautological fact. So in other words, this will go here, right? Now I'm calling this function here x equals inc t, so I'm passing t as a parameter. So t as a parameter will be passed here, so t will flow to v, right, in this case. And then after this statement, again, I'm going to propagate things forward using IDE. And these functions here are going to be propagated forward using IDE, because I'm basically doing plain assignment of t to v and this tautological fact to the other tautological fact. So I'm using IDs for those. And then again, v here. So remember, applying our functions from here, basically applying our functions here, v is propagated forward using the ID, identity function. Then r here is going to be reachable from v using the function I equals I plus 1. So this is the application of the method summary from before to that method here. To that example here. Now if I move this forward to the point right before the next statement, I'm going to use ID, ID, ID. And then the return of R, well, that doesn't cause anything to be happening. So again, all these are going to be propagated forward after the statement. You will notice in this example that I have a point before each statement and after each statement, just so that we know the effect of where exactly the function that is being applied has an effect on the statement. Because before we just extend an edge from one statement to the other. So here I'm being a bit more explicit about the nodes that I have in my exploded supergraph, just to be clear where those functions apply. So here after the return of that function, I would be done with that propagation within that function, and then I would return again to my main program. The other thing here that we can just do now is this. Basically, the tautology fact is always reachable from everywhere, so there is no point in delaying that or not showing that now. And in fact, in many cases, this tautological fact is not even shown in the exploded supergap because it's really redundant and it's a bit confusing. So you might not even see it in many examples as we go. All right, so now we have functions for most of the edges here. But there's one thing that we want to compute, right? So you remember, in phase one, we need to compute the method summary. So how do we compute the method summary here? We want to compute some summarization for the effect of that function here. We're going to do that in a similar way to what we did with IFDS. So just give me a second here. Hopefully I'll be able to copy over all this in a second. That didn't work so well. There we go. Much better. There we go. So how are we going to create our method summaries here? So the way we're going to create the method summaries is doing something similar to the exploded supergraph on the fly exploded supergraph construction. In other words, the thing that we want to compute is, so in IFDS, if you remember, we computed path summaries. In IDE, on the other hand, we want to compute something called jump function, which is the equivalent of path summaries or path edges, sorry, in IFDS. So in IFDS, a path edge was that edge that summarizes the path from the tautological fact to that point, to the current point in the program. Jump functions are going to do exactly the same thing, but for IDE, where you have function annotations on the edges rather than having just data flow facts that are propagating from one edge to the following. So here's how we're going to do this. And I'm glad that I spent some time at the beginning of the lecture to explain the self loop, the initial loop, the self-initial loop, because here's how we are actually going to use that here. So for that tautological fact to be reachable, we're going to self-initialize it with ID, because it is initially reachable from everywhere, right? And we're still going to have ID here, an ID here, an ID here. And then, let me just color code some of those functions so that when we have the next computation, we'll know what it is. So this is I equal to 0. This is the first identity function that we have. Here we have our ID. And in this function here, we have lambda I equals I plus 1. And then we're going back here to that example. So what would our jump function be? So our jump function basically after this statement is something that will summarize this path up to that point, right? So something that will summarize this path up to that point. So what are the functions that we have along this path? So the jump function that we have along this path, I'm just going to call this JF, are basically ID, lambda I equals 0, and then ID. Remember from our monotone framework lectures, how do we represent functions along the same path? What is the operator that we're going to use to combine functions along the same path, to have a function that represents that path? Yes, it's function composition. So we're going to do the same thing here. So we're going to compose all the functions along the path that we have so far to get our jump function, or our the equivalent of the path summary or the path edge up to that point. And in this case, well, ID composed anything is basically just eliminate that. So our jump function here would be lambda I equal to 0, which is our jump function of that point. So if I want to represent this path here, which I'm going to maybe highlight with the color red, this one here, this is going to be the jump function that represents it. So I can basically eliminate all this edge here and just have one jump function that says lambda I equals to 0. We are beyond our class time for today, unfortunately. But on Thursday, I will continue discussing how we can create more jump functions and more summaries for in an IDE for each path, and how we're going to combine all those paths together, and how we can eventually, after all these combinations and function compositions, we get a method summary, and then in phase 2 of IDE, how do we actually use that method summary to apply it to some program, to that program that we have at hand here. And how that would allow us to actually do linear constant propagation without having infinite domain. It was a pleasure talking to all of you today. Have a nice rest of your day, and we're going to talk again on Thursday later this week. Thank you all. Have a good day.